Okay, let's get going. This is Talk 4.4 on sepsis. What is sepsis? This is a life threatening organ dysfunction due to a dysregulated host response to an infection. Okay? Then you can also hear shock associated with this as well, which is just ischemia or a decrease in tissue oxygenation. And you will see as we go through sepsis how this occurs. Okay? But what does this mean? That's kind of a broad statement. Well, any infection has the potential to seep into this sepsis territory. Basically, it's not so much dysregulated as it is just body wide. We don't want it body wide, so there's where you get the dysregulation from. But the neutrophils and the macrophages and all your cells aren't acting incorrectly per se. They're just reacting to a stimulus that's everywhere. All right, so it's usually bacterial, can be fungal or viral. All that matters is it's kind of gotten into the blood now. And we have a huge viral, bacterial, or fungal load in the blood, stimulating all of my white blood cells, causing them to secrete inflammatory compounds and causing them to, commit apoptosis and release their insides in an attempt to quell the infection. But little do these white blood cells know that the infection is everywhere. So it fights it like normal. The innate cells respond, cytokines recruit more innate cells. This becomes really problematic once the pathogen gets into the blood, once it starts getting septic. So white blood cell recruitment, these WBCs release compounds that I just said, recruit more. They cause vasodilation. So the blood vessel gets wider. It gets wider. Right, this is good in cases of white blood cells acting normally. What they do is they help fight infection. I want more blood to get to that area to transfer more white blood cells to that area. So usually vasodilation is optimal. In this case, not so much. And then in that same vein of thought, we have the increased vessel permeability. Usually infection is occurring in the tissue space, so outside of the blood vessel. So we have that whole process that we talked about in Unit 1 called extravasation. Extra meaning outside, vas meaning blood, so getting outside of the blood vessel. So making my blood vessel leaky and easy to leave is advantageous, just not when it's everywhere in the body. So what happens is our SVR, our systemic vascular resistance, drops, which drops our blood pressure. So now we are hypotensive. And to boot, these leaky vessels are causing fluid loss. So we are hypovolemic. I just simply lack blood volume now because I'm losing all of this fluid to the interstitial space. Okay, because my fluids have almost like holes in them for all intents and purposes. Okay. So what's going on here? Well, we have some sort of breach. I have Captain America's shield all broken. Please don't sue me, Disney. We have a microbe, a fungi, or a viral load, be it because maybe an IBC was formed, so I have a big old bacterial colony that just releases and overloads all of my innate containment mechanisms, and then it gets into the blood. Right? We talked about with UTIs at the beginning of the year, a very, very rare case, obviously, but a E. coli could maybe travel all the way up the urinary tree to the kidneys, cause some pyelonephritis, and potentially get into the blood that way. But a lot of innate mechanisms would have to fail, right? Your whole genitourinary epithelium would have had to fail you. We'll talk about a fungi infection later this unit, but most of these are from like spores and mold that are usually easily protected against by a regular immune system. So this only really happens with immunocompromised individuals. So a big thank you to our immune system. We don't really know how many diseases that it protects us against, right? Even if, you folks are taking this class and I've had to do a lot of reading and research for this class, even I have no idea how many diseases that I've been protected against. And this was just one of the new ones that I found. Not to say that I've been around these spores, but who knows? You just never know what kind of defenses your body has put up the shield for. So that's just so cool to think about. All right, so local infection becomes systemic. So failure of containment, overwhelming inoculum, again on the idea of maybe we have just a gigantic load of bacteria that the cells couldn't contain. We detect PAMPs along with these nasties, releasing pro-inflammatory cytokines in response. Remember, that was the whole arc. PAMPs detected by PERS, and then that causes AMP, antimicrobial peptide release. So that arc, all the way back in lecture, like what was that, 1.3 or 4? And whatever, it's coming back now. I can't stress this enough. This is one of the biggest drivers behind the physiological toilet bowl that we find ourselves in with sepsis. Vasodilation and capillary leak, both of them being persistent in this case. So inflammatory cytokines, we have a nitric oxide release from the endothelium of the blood vessels, causing further vasodilation and disruption of those tight junctions that kind of link the cells of the blood vessel wall together. So that gives us increased vascular permeability. So my BP is decreasing, and my volume is decreasing, which also decreases my BP. So it's just a compounding effect here. And I have that here. Decreased systemic vascular resistance, increased permeability. Another thing that I haven't mentioned yet, though, is a decrease in oncotic pressure. What's going on here? Well, I have plenty of plasma proteins in my blood, most notably albumin. That's like the big one that we talk about, and a real establisher of oncotic pressure. Basically, having a concentration of this protein in here, the natural tendency of water and just chemical solutions in general is to reach an equilibrium. With outside of the vessel, okay? Or any type of semi-permeable membrane. That's just like the fundamental biology there. So when I see a little bit of albumin in the vessel, water is going to want to seep in and try to dilute that concentration because I have no albumin outside. So that is where we get oncotic pressure, that pressure driving fluid from the outside to the inside. But if I'm losing my plasma proteins, if I'm actually creating equilibrium, basically, because I have all these holes due to permeability, now my albumin is outside. So now I have no driving force to dilute the albumin inside. Thus, I have no oncotic pressure, or a decreased amount, if you will. So that further messes up the tight balance that we had between hydrostatic and oncotic blood pressure, or oncotic pressure, sorry. Another big thing to think of. So I mentioned early on, neutrophils are excellent at being our first responders, getting to the site of infection as quick as possible. They lack nuance. They lack specificity. One of their main mechanisms is the nets, right? The neutrophil extracellular traps. That's literally made of their DNA. Right, so they're throwing their nucleus at a pathogen, and obviously the cell can't live without its nucleus, its brain. So this is an apoptotic act. Not only that, but the neutrophil releases ROS, reactive oxygen species. You can think of them as oxygen anions. You can also think of them, I have Neo over here, as bullets. Okay? I don't want to get too into biochemistry weeds here, but having free oxygen anions floating around where a bunch of delicate cellular metabolism and oxidative phosphorylation is occurring, that's really, really detrimental. It's bad. It can lead to what we call oxidative stress. Your body can only handle so much of that. So again, your neutrophils are awesome for getting to this site of infection early, but I just have all of these enzymes, nets, or the nets themselves aren't bad, but that causes apoptosis. So any proteolytic and inflammatory granules and enzymes are now in the serum, are now in the blood. And again, this infection's body-wide, systemic. So this is happening everywhere. So all of these toxic compounds are circulating everywhere. So that's further compounding this effect here. We have collateral damage. Well, what are the consequences? We damage the vessel wall, right? That's not good. My roads that lead and connect on my entire body are now getting chipped away by my very own machinery. So I have disseminated endothelial injury, exposing that basement membrane. And if we remember anything from, I think it was lecture 2.3, that was the clotting cascade. When I have exposed basement membrane, I have exposed collagen. Exposed collagen leads to the binding of that von Willebrand factor. And now I have clots disseminated. I have clots everywhere. Oh no. Oh no. So these micro abrasions, so these little nicks on my blood vessels everywhere, is inciting thrombin generation. The anticoagulant compounds are suppressed by all the cytokines in the area, and fibrinolysis, so the breakdown of the clots, is inhibited as well. It's a very delicate signaling pathway with all these clotting factors, and if I have all these inflammatory cytokines and all these cells freaking out trying to contain this infection, well, this gets drowned out. So now these clots are persisting maybe longer than they should. And then here's that diagram from from a couple units ago. But that's the endothelial cells that compose the wall of the blood vessel, and I'm breaking those down, exposing the basement membrane underneath that has these little von Willebrand factor tags on them. Once those get tagged, well, then I get platelet activation, and then I start forming clots and getting more platelets to the area. This is happening everywhere. Disseminated intravascular coagulation, DIC. Okay, I made the funny joke in class. I'm not going to make it online. Widespread microthrombi leading to tissue ischemia, right? Think about, let's go all the way back here. If I'm throwing clots like everywhere, at the capillary bed, this is one cell thick usually. Very, very tiny vessels here. So if I'm having clots everywhere, then I'm knocking out an entire capillary bed because this is now blocked. So everywhere downstream is now ischemic. I can't get oxygen diffusion on this whole capillary bed now. So this is happening in a lot of places, and it might be happening at the organ level, right? So if for whatever reason, if it gets localized in the lungs or in the liver or in the kidneys, then you're going to have intense problems there because now that organ isn't getting blood. And conversely, I'm using my platelets and clotting factors like everywhere, right? I'm not forming those micro abrasions. My body thinks I need to start forming clots absolutely everywhere. And my liver, which is what makes my clotting factors, it just can't keep up with the constant clotting. So actually, these patients have a bleeding risk as well, because if bleeding in the actual sense, not in the microabrasion sense, but if you actually had a cut, there's no more clotting factors to go around because I'm using all of them. All right, at the organ level, like I was kind of referencing here, if that organ isn't getting correct perfusion and nutrients, well, that organ is going to start to fail. What does that look like in the lungs? ARDS, acute respiratory, oh no. What was that called? Give me one sec. Doing great. Distress. God, why couldn't I think of that? Let's write it down then. Why don't we have it bloody written down? Acute respiratory distress syndrome. So the capillary alveoli, or the capillaries to the alveoli that participate in that gas exchange, those are just getting ruptured. They're broken down. Now, I'm not getting oxygen. I'm not getting correct perfusion to that area. So, yeah, we have respiratory distress. In the kidneys are the Brita filter of the body, sectioning out the fluid and getting rid of nitrogenous waste, maintaining ion balance, and maintaining acid-base balance. And they have a really good interface with the blood because, well, that's where my fluid is. If those the kidney cells, the nephrons, if they are constantly just getting inundated with inflammatory molecules and reactive oxygen species and just getting beat to death, and not to mention not getting proper oxygen and nutrients, well, then the tubes, the PCT, the beginning of the nephrons, they're just going to break down and start dying. So the whole function of the kidney, right, that filtration of the blood and of the fluid is now diminished. So now I'm running into the potential for kidney failure. And again, thinking of what's going on in the blood, well, you have toxins going on, going all throughout the system. So now add to it that your filter isn't working. Right now add to it that you can't get rid of nitrogenous waste. So just as we can see, this toilet bowl keeps getting worse. Or potentially it's locked into the liver, and then the liver can't do liver things. Big thing with liver is detoxifying, right? You always think about that. Common example is just having a beer. You got to get rid of those ethanol groups, or you got to do some biochemistry to them. Now you can't do that. If you're septic, you're probably not partying, having beers, but you know what I'm trying to say. Liver makes bile for us. Now that's diminished. Your fat metabolism is going to decrease. I can't make any coagulation factors. So maybe this will help with that disseminated intravascular coagulation. I'm kidding. It's probably also still not good. Not to mention, liver's involved with your plasma protein secretion as well. So that messes with my albumin levels too. So can we see, just it doesn't matter what organ you hit, right? It is going to compound and be very detrimental to the already stressed condition that the body is in. And the gut, right? If we break down those tight junctions, maybe my gut flora, that it's fine to have those in my small intestine, my large intestine, helping me break down fiber and things like that. But if my gut flora goes into the blood, it's still bacteria, right? It's still going to cause problems. And in the brain, maybe that blood-brain barrier becomes permeable, and now I have a cytokine storm going on inside my CNS. Well, then you're going to have altered mental status, right? Then your neurons aren't going to be firing properly. That is a very delicate mechanism, as you could imagine. And, setting fire to it is probably not advantageous. All right. So the whole point of this is when these get set on fire, it's not good, right? Pretty self-explanatory. Okay, last little bit here. So fluid resuscitation failure. You would think if a patient is hypovolemic, if I'm seeing that they're losing fluid, well, let's just give them fluid, right? But no, the capillaries are still leaky. They are still getting those inflammatory signals like from histamine and heparin to be leaky. So if I'm not getting rid of that stimulus, then just adding more fluid I'm just adding more fluid for it to ultimately leak out again. And we have constant nitric oxide production, again, due to this inflammation, so constant vasodilation, persistent hypotension, because the fluid resuscitation just will not take if these don't go away. I have mitochondrial dysfunction, mitochondria, the storm of cytokines, not to mention the reactive oxygen species, so those free radical oxygen anions floating around, messing up your typical biochemistry, right? I can't perform correct oxidative phosphorylation, which is the end, what happens at the electron transport chain, the end of cellular metabolism. So I can't do aerobic respiration. I can't make my ATP the way I like to make it, the most efficient way. So now I have to do anaerobic, And the whole point, the whole detriment to that is a buildup of lactic acid. Now I got metabolic acidosis. So you see that there's another level of compounding effects. Now another level of, I guess you could say, toxicity to the blood. Now it's acidic, right? I want to maintain a relatively neutral pH, and now I'm adding another stressor to the event. Okay. Then that ultimately ends in this multi-organ failure, right? So we have this common triad of ARDS, so that's the lungs, acute respiratory distress syndrome, acute renal failure, and hepatic dysfunction. That's usually the common triad. And as you can imagine, if all three of those organ systems are failing, well, it's not going to look well prognosis-wise. Extremely high mortality rate there, unfortunately. So, signs and symptoms. I saw fever and hypothermia, so I think just temperature regulation gets a little bit whack here. And tachycardia and tachypnea. So that is increased heart rate. And increased breath rate. All right, so since you are hypotensive and hypovolemic, you're going to try and increase that cardiac output. One of the ways to do that, increase heart rate. And since we're sensing some ischemia or some low oxygen delivery, I'm going to breathe more and try to get more oxygen out the air. One of the bedside scores we can do, this is kind of impromptu, but infections, they technically can all run the risk of becoming septic. So we should have this on the back of the mind, right? We don't want to potentially miss this becoming septic. So there's a quick called the Q-SOFA score you can do, and you check these three things: AMS, altered mental status, right? If this thing is going body-wide, if it's affecting cognition or any type of abilities like that, we can check that. Maybe with like the Glasgow scale. A respiratory rate above 22 breaths per minute, or a systolic BP under 100. If you check 2 of these 3, or 3 of these 3, you are at high risk. And then we probably run some more tests to determine if sepsis is occurring. But that's the Q-SOFA score. All right, and lastly, just to tie things off and hammer home a good point that I think is important to know, the 2 phases. We have an early phase of this septic shock and a cold phase, or late phase. First up, vasodilation, hypotension. I've beat that horse to death. Vasodilation and permeability leading to hypotension and hypovolemia. So we drop our blood pressure. One of the principal determinant of blood pressure is cardiac output. So I'm going to try and increase cardiac output because that will increase my blood pressure. So in this state, the patient would look, or they would appear, they are warm to the touch because all of these vessels are open and leaky, and they'd be flushed because, again, these vessels close to the skin are going to be open, leaky, so you'll see some redness. Late phase, keep in mind, during all of this, leaky vessels lose fluid. So I'm losing blood volume to the interstitial space this whole time. If you know anything about cardiac physiology, one of the things that I require for good cardiac output is something called preload. That is heavily determinant on venous return. If I'm not getting nearly as much venous return as I would if I didn't have leaky vessels, right? Well, then I can't really increase my cardiac output because I'm not getting good amount of blood back into the heart. Okay? So despite my best efforts, my cardiac output is still just not getting to where I want it to be. Okay, so my body is getting the signals to increase, but I'm hypovolemic. I don't have enough fluid to do that. So what we call this is just persistent hypotension. Despite getting the signals to say, hey, can we help things out? I can't. I literally can't. The fluid's not there for me to do so. So that hypotension is persistent, and because it is persistent, I have poor perfusion. So I'm not getting adequate oxygen and nutrients to the organs and to the tissues. Well, because my blood pressure is not high enough, and likely, if it's damaging the lungs, my oxygen content isn't that high either. So a whole slew of damaging effects all coming together to create some nasty chorus of unfortunate physiology here. But I think it does also help appreciate why vasodilation is helpful and why permeability can be helpful, but it also shows that these mechanisms aren't meant to be used body-wide. So like a lot of things in life, we need that ebb and flow, that homeostasis. We don't want to go full throttle. And I hope this shows you guys how detrimental and how powerful your immune system is, but it needs to be pointed and regulated and used in the right spaces only. Okay, so that is 4.4. Thank you guys very much